My bad. Forgot to turn on the mic. So, makes the beginning of the lecture so much more fun. And all this great content to say too. Let's give you my life story. And guess you missed that part. We've covered a lot of material so far this class. Okay? This is 2 weeks in and we're really hitting the material hard. You need to make sure you're comfortable with the material. Okay? Why do we use the equations the way that we do? Why is it that node voltage analysis have something to do with component voltages? Why was the relationship between power and current? And there's a lot of terms that we're using in this course. There's a lot of framework to how we develop solving problems in this class. There's just a lot of work that we have already done. This is week 2. It only gets harder from here. So, my advice to you, go back through the videos I've already posted. Go back through your notes. Study your notes, okay? I'm not going to be here this week because, thank you, jury duty. When I get back next week, I'm going to expect to answer some questions about everything we learned. Just as a hint, next week we're currently scheduled to have Raspberry Pi stuff. I'm going to go ahead and push that back a week. So we'll start on Raspberry Pi stuff the week after. Next week we're going to continue our discussion on resistance-only circuits because I think that's really important for us to really dive deep into that material. There is a lot to cover when it comes to resistance-based circuits because a lot is, what is this constitutive versus component equations? What are all of these node voltages? What do they mean? But that's where we stand. Hopefully things will start to make more sense by next week. We'll give some time to do examples. We'll do some hard examples. And you're going to have a lot of homework to do. You got to keep up on your homework. Because otherwise this class will eat you alive slowly but surely. So, keep that in mind. Now I will say that this has been this is a fun group. I'm excited for the remainder of this course. I wish the first 2 weeks didn't suck so much because I can't even see you all. This kills me. I hate virtual recordings. But we will have a good rest of our semester. This is going to be an exciting semester. We're going to build some cool stuff. We're going to get to play with some cool stuff. So just hang on. It gets better, but you just have to make sure you're doing the work for this class. If you're not doing the work for this class, you will fall behind. All right. So today we're going to talk about a little bit more we're going to talk about a little bit more in depth of a topic. Now I will say I am not going to be giving you any homework over this, but this lecture is important because it identifies some of the discussion topics that are really critical to understanding this topic as a whole. You want to gain more understanding about resistance-only circuits and how to solve them. This is really critical. We don't require you to have matrix, an understanding of how to use matrices. If I taught this class a little differently, I would probably add matrix evaluation as a piece of this course because it is really foundational to understanding what we do and really hashing out a lot of the material there. That said, I'm not adding matrix evaluation into this course. I'm not going to be teaching you matrix evaluation. For those of you who already know matrix evaluation, hopefully you can figure out how to do some of this. If you want to do this to solve your homework problems, great. It'll save you time and it'll save you life. But I'm not requiring you to do this, and I will not ask you to do this. I'm just giving you another tool, and I'm just giving you more discussion, try to give you a better understanding of why it is that we do what we do for electrical analysis. Okay, so when it comes to node voltage analysis, the basic idea behind this is if we find node voltages, which, if you don't know what a node voltage is, it's basically if you have a node, let's say here's node 1, node 2, node 3, node 4, and they're all connected by some kind of a component. Okay, we can identify what each of these voltages are relative to our 0 point, or relative to where we identify as ground. So I could say this is ground right here, and I can calculate all of the voltages relative to node 3, or I could identify them relative to node 4. Basically what we do is we set, of course I'm going to have hiccups all of a sudden, great. We set one node equal to 0, and then we evaluate all of the other nodes relative to that one node. So that's all a node voltage is. You take a measurement relative to that node. It would be as if you have one lead of a multimeter touching node 3, and then you go around and you measure every other point on your circuit relative to node 3. We're actually going to do that for lab 1. But it is what it is. Okay, so if we find what the node voltages are relative to ground, we solved the circuit. Why? Because we're not going to be dealing with a case in this class where you don't understand the resistance. Nobody is going to build a circuit and then not understand the resistance. Okay. Now we can measure, find voltages, figure out currents. We can solve for a lot of these things. If you don't know what a resistance is, you can find what the current is, you can find what the voltage is, and you can figure out the resistance there using Ohm's Law. That's something where in this class we're just always going to know what the resistance value is, because usually we're treating this course as if we're you could measure resistance and find it out. Resistance is one of the easiest pieces to find on anything. But we're gonna mostly be dealing with classes if the resistances are known. So because the resistances are known, if you can find what the voltages are, you can find what the current is going through that component. Again, Ohm's Law. Okay, so this is a really easy way of doing this, okay? Major concept here. Your voltage through each component is equal to your nodal voltage coming in minus your nodal voltage coming out. We've used this equation already a few times in this, in the lectures that I posted. But when you have a voltage across a component, it is as if you've got this node here, this node here. You put your multimeter lead in here, you put your multimeter lead in here. You're measuring a nodal voltages difference, and that gives you what the voltage is across that component. Okay, so this is kind of foundational for our understanding of this course. Okay, so keep this in mind. This is something you're absolutely going to need to know. But now, if we can find out what the node voltages are, this is our relationship to the voltage across the components. So if we find our node voltages, we'll figure out the component voltages. If we have our component voltages, we can use the component equations, which, by the way, since these are resistance-only circuits, they're always going to be Ohm's Law. You only have one component equation that we're going to be dealing with until we start getting into capacitors and inductors. This is it. So if you have one component equation and you have this relationship here, all you need to do is solve this. You know this, you can figure out the current. Okay, so easy relationship, easy work. Okay, now node voltage analysis is a little bit different than mesh current analysis. I'm going to briefly touch on that. I hate mesh current analysis because it involves a little bit more of a fine discussion into a piece that I don't like. So this is the case. All right, so we're going to start with a very simple node voltage system. Okay, you have 4 nodes, one loop. One loop goes around the center. Here's R1, here's R2, here's R3, and here, because this is a direct DC voltage source, we're going to write it as Vs. Okay, so we have these four components. We have these 4 nodes. According to node voltage analysis uses the constitutive equations that are, you have your KVL. Oh, by the way, constitutive equations, they are always the same for it's always KVL and KCL. So, writing out my constitutive equations identify the system. As you'll remember, in KVL here you have negative Vs plus VR1 plus VR2 plus VR3 is equal to 0. For KCL, I'm going to go ahead and simplify this just because I don't want to write down all of the equations which all lead to the same thing. IS is equal to IR1 is equal to IR2 is equal to IR3. You can figure that out because they're all in series. Okay? But if you really want to write out all the KCL equations and prove that this is true to yourself, knock yourself out. Okay? Dare you, question me. Try to figure out how I got these. Okay? I showed you how to use KCL analysis. Yes, I do cut some corners to save time on videos. Okay, so these are all true according to the KCL equations that we have. Okay, 1 in, 1 out for this one, 1 in, 1 out for this one, 1 in, 1 out for this one, 1 in, 1 out for this one. They're all true. They're all equal to each other. There's only one current flowing through here because we only have one loop. Okay, so this is our constitutive equations that we have. Now, the beauty of this is that we also have a bunch of nodal equations that we can come up with too. So instead, if we really wanted to rewrite this system, we could write them as our component equations, which we have our component equations. And those are VR1 is equal to IR1 R1, VR2 is equal to IR2 R2, VR3 is equal to IR3 R3. Now, as we've shown, we can actually solve this system by turning this into an equivalent resistance, coming back in, plugging in what we know, developing our system from there, okay? We can do that. That's fine. Another route that we can go is, instead of adding those additional equations, we can add nodal equations. Okay, the nodal equations here now are V1 minus V2, which is the voltage across from node 1 to node 2. That's equal to VR1. Okay, that's it. And then we can also say V2 minus V3 is equal to VR2. V3 minus V4 is equal to VR3. And then V1 minus V4 is equal to Vs. Okay, the nodal equations, they add 4 different variables, V1, V2, V3, V4. But it also gives us one more variable that we don't know, and that is we'll go ahead and define 4 as ground, which is the number 0. Why do we do that? I usually attach ground at the negative end of our power source, because it allows us to then have a circuit where all of the node voltages are positive. So there's a method to my madness. If you were to attach ground up here, it would still work, yes, and you can do that in a circuit, but all of your node voltages are going to be negative. It's just the way that it works. Which is gross, and it does create some issues by limiting the source voltage, just by the way that source voltages are made. They're made to have the ground connected to the negative end. Just saying. In any case, you can put that ground wire anywhere. You can put it over here, you can put it over here, and then you're just measuring relative to a ground value that is 0 somewhere. So here, because we're adding in node voltages, it allows us to write a 0 here, and then we end up with 3 free equations, which is awesome. And extra equations, that actually does give us enough equations to solve the entire diagram. So that's the idea behind node voltage analysis. Now, I'm not going to get too heavy into matrix theory here. But if you take this, combine it with this, and put it into the constitutive equations, what you end up with is these allow you to have common terms. So here I could just define everything as IS, and then I can write everything in terms of IS, which completely eliminates all of other I values. Okay, so now we have our V values are equal to some value of current times the resistance, which means when I go to plug them in here, I just have some value of current times the resistance. Well, I don't know what the value of the current is, but I can figure out what that value of current is by solving for this matrix value. So fun times here. Additionally, we can use this equation to identify what the correlation is between all of them. In any case, you end up developing a matrix where a matrix is a series of organized numbers all put in very specific location in order to perform a very specific mathematical function. So you have all of these together, you multiply it by your node voltages, V1, V2, V3, V4, and then you get a constant value out of this. This is the goal. Now, if you solve this matrix here and you turn it into its reduced row echelon form, what you end up with is you solve this matrix and you get an identity matrix using reduced row echelon form. This multiplied by this will give you your four numbers. Okay. By the way, RREF, the reduced row echelon form, that reduces whatever the numbers here are into the identity matrix. That's a command that you can issue to your calculator, which makes things so much simpler. So you issue a command to your calculator, solve this math function, and then you get spit out what the answers are for the node voltages. It's that easy. So this is amazing. This truly is one of the best pieces of analytical tool, because you're really relying on your calculator to do all the math for you. And it's super simple. If you know how to do matrix analysis, would look more into this, look at the examples in the book. But this is simple, okay? You end up reduced row echelon form. No, I won't get ahead of myself. We'll go ahead and derive the matrix for this. And then we'll move on to talking about mesh current analysis, the differences between the two. Because again, that's something that's really important to understand. It's another tool that you can use to evaluate your matrices. The nice piece about node voltage analysis is that all systems will work like this. All of them. Okay? Mesh current analysis does require that the system be planar. I'll discuss that. But this works for every system. Absolutely every one. And can work for a 3D system if you really want to. Okay, so we have this setting here. What our goal is we want to put it in the format of some numbers multiplied by a function of V1, V2, V3, V4 is equal to some other number, okay? So in order to get this to be a matrix, what we do is we have some function of V1, V2, V3, and V4 is equal to some number. Once we have four of these equations, we have our matrix, and then we're done, okay? Now you'll notice we have four different nodes, which also means we have four different KCL equations. I probably should have written all of these out. Dang it. Flim flam. Ugh. I'll write them out now, because here I was saving all this time. So for node 1, our nodal equation is 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 equal to IR1. For node 2, our nodal equation is IR1 is equal to IR2. For node 3, we have IR2 is equal to IR3. And then for node 4, we have IR3 is equal to IS. Okay. So those are our 4 equations. Guess what? Those are going to be our 4 matrix equations. They're the KCL equations. You're going to have the same number of equations as you have the number of nodes. And really, we're not going to deal a whole lot with KVL. KVL is just going to allow us to identify what is IS. And that is, that's another really important piece here, because otherwise, what is IS? What does that mean? It's not really useful as it is right now. So here's our goal. Now I'm going to go ahead and take the 2 easy equations, which are the ones that don't have IS in them at all. Okay, we'll combine them in with these, and we'll combine them in with our component equations. Okay, so here we have IR1 equals IR2. Okay, now the nice piece about IR1 and IR2 is we can look at our vast series of equations that we have written out on the board here, our constitutive equations, our component equations, and then our nodal equations, which are also constitutive equations. We can, well, because these nodal equations are basically just, well, it is what it is, but whatever. We can take all of these equations, and anytime we see IR1 or IR2 in any of these, we can go ahead and plug them in. Now, do you see an IR1? That's right! It's right there! I hate it when TV does that. It just made me feel like I was an idiot. So I do it to you, so you can feel like an idiot too. Anyways, we see IR1 and IR2 in the component equations right there. So we can use those. So we can just replace that, rearrange it a little bit. Instead, now instead of IR1 equals IR2, we have VR1 over R1 is equal to VR2 over R2, which is, that's nice. Okay, that's sweet. Now we can put those directly in terms of our nodal voltages. VR1 and VR2, we've already got those. So we just quickly replace those with V1 minus V2 over R1 is equal to V2 minus V3 over R2. Okay, and now this is a function that only has V1, V2, V3, V4 in it. Great. We'll rearrange this so that we have it nicely on one side. Then you have 1 over R1 times V1 minus V2. Oh, no, we'll say plus 1 over R2 minus, no, I guess it's a minus. Negative 1 over R1 minus 1 over R2. Because if we bring it to this side, they both become negative. Times V2. And then this also becomes a positive. 1 over R2. V3 is equal to 0. So now we have some function of V1, V2, V3, V4. V1, V2, V3, V4 is equal to 0. Nice. That's it. And we just have to keep going. Now the IS is going to pose a problem. I'm going to show you how to deal with that. But this ultimately it's a much simpler way of building these equations. If you understand how to do this method, that doesn't require you to have to do equivalent resistances. Okay, so 1 over R, well, we've already dealt with this. We'll go on to the next one, which is IR2 is equal to IR3. And if you have IR2 is equal to IR3, and we replace IR2 and IR3, we just get rid of them here. So you end up with VR2 over R2 is equal to VR3 over R3. We replace these two with our nodal voltages values. This basically you're just trying to get it into voltage, and then you take the voltage and you convert it into current. So that's awesome. So we have V2 minus V3 over R2 is equal to V3 minus V4 over R3. Sweet. That's wonderful. If we rearrange this, we'll get 1 over R2 times V2 plus negative 1 over R2 minus 1 over R3 times V3 plus 1 over R3 times V4 is equal to 0. That's sweet. So now we have 2 equations. Well, the problem is that we also have these 2 equations here, which are kind of gross. So we're going to ignore them and we're going to pre-solve them to figure out what IS and IR are. You know, we can pre-solve them because we already know what V1 is. V1 is equal to Vs. So we know that V1 minus V4 is equal to Vs. That's this equation right here. We can solve that equation because we assume that V4 is equal to 0, which, by the way, one of our equations is actually V4 equals 0. We have this one that has V1, V4, and it equals Vs. We ignore the Is entirely because we weren't given Is, we were given Vs. So we need an equation that has Vs in it, not Is. And then we set our 0 value, and that's it. We're done. We're completely done. We've solved this whole thing, and we didn't have to do any of the equivalent resistances. Okay? So here we have V1 is equal to Vs. We'll take our Vs value. We have V4 is equal to 0. The matrix that we end up coming up with as a result of all these, just going to erase this so that we can talk voltage values. The matrix that we come up with is we have our 4 equations, okay? Here's 1, here's 2, here's 3, and here's 4. Okay, now all of these are independent because we can't derive another one off of it. That's another matrix, piece of matrix math that you do have to ensure. And that's also one of the reasons why I just took these 2. But you end up actually solving these 4 equations, but whatever. Anyways, we have all of this equations, all we just have to do is plug it in. So here we have our V1 term, V2 term, V3 term. So this becomes 1 over R1, negative 1 over R1 minus 1 over R2, and then 1 over R2, and then 0. And that gets multiplied by V1, V2, V3, V4. Ends up equaling 0. Okay, that's our top equation. Next equation, we'll go ahead and take this one, which is 1 over R2, and then we have negative 1 over R2 minus 1 over R3, and then we have 1 over R3. Oops. I needed to shift all these over because that starts with a 0. 1 over R2, negative 1 over R2 minus 1 over R3, and then 1 over R3 times this is equal to 0. Okay, then we have this bottom one, which is our V4 equation. 1 times V4 is equal to 0. And then we have our last one, which is V1, 1, is equal to Vs. And that's it. You plug this into a calculator, you solve that, you have the entire system. You have all of the nodal voltages. You can take those nodal voltages, use them in this way, and figure out your components. Okay? So that's a very simple example. They do get more complex, but they don't actually end up getting a whole lot more complex. You have your nodal voltage equations, and you just keep using them. The end. Combine them with your constitutive equations, combine them with your component equations. You end up solving all of them. Okay? Once you have 4 functions, 4 independent functions of V1, V2, V3, V4, you just plug it into a calculator, you solve it. Okay? That's node voltage analysis. Makes this so much simpler, makes this all automated. I like automated systems. Okay? So, again, I'm not going to be requiring you to do it this method. Everything that we're going to be doing in this class is simple enough that you can use equivalent resistances to solve them. But it's an important method to also understand. Why do we do it this way? So we'll move on to the next topic quickly, which is mesh current analysis, which is a whole lot like this, because we're going to be developing a matrix. But it does have a few different concepts in it. And those concepts are things that I think should be addressed because it's an analytical tool that's used in current electrical engineering, and you should be aware of it. Okay, I wouldn't feel comfortable teaching this class if I didn't give you a thorough discussion there. Now the important piece to keep in mind is you have the mesh current analysis which is going on, which is basically mesh current analysis. Okay, in mesh current analysis what you have is the idea is you're going to solve mesh currents to solve a system. Okay, last time when we did node voltage analysis, we were solving for nodes, node voltages. Now we're actually solving for mesh currents. Well, what is a mesh current? There's a reason why we haven't talked about it a lot in this class. It's because I really hate mesh currents. But we're there. This will give you a little bit more perspective on what a mesh current is. So let's say I'm going to have a current source. And let's say I have four resistors hooked up like this. Okay. Now the way that I've taught you so far in class is to say, oh, this is loop 1, this is loop 2, this is loop 3. Okay, and yeah, that's true. All of that is true. 100% of this is accurate. In mesh current analysis, what we can say is we can say that there is a mesh current 1, which is associated, I'm going to call it IL1, that is associated with a current that is traveling around the loop of 1. Okay? And then you have IL2 and IL3. There is a current traveling around the loop in 3 and a current traveling around the loop in 2. Okay? We assume that they're clockwise, and that's how we develop our equations. It's the reason why I introduced them to you in a clockwise fashion, is basically to build into this discussion of what is a mesh current. Okay, so we have each of these three currents. What we have to do then is we have to say, all right, now this is going to teach us something. What components are involved in here? Well, this current that's going around loop 1, it does involve the current that's going through component 1. We'll call this R1, we'll call this R2, we'll call this R3, and we'll call this R4. Okay, we've got these three mesh current terms, and if we put everything in terms of these, what we'll find is that, okay, when we did our component diagram, which loops contact which components, I had you draw those out. We'll go ahead and draw that out again. So here, component, we have a pos node, positive node, we have our neg node, which is the negative end of the node, and then the loops that are associated with it. Okay, so here we've got our 5 components, R1, R2, R3, R4, and then IS. Okay, the positive node for 1, we'll call this 1, we'll call this 2, this will be 3, this will be 4. Okay, so positive node for R1 is going to be 1, negative node is going to be 4. Positive node for R2 is going to be 1, and it's going to go to 2. For R3 is also going to be 1, go to 2. R4 is going to be 3. My apologies. This is all 2. So I'll replace that with 3. So go from 2 to 3. And then IS goes from 1 to 3. Okay. If we talk about loops, R1 is only associated with a positive, no, it's a negative in loop 1. Okay. And I'm going to show you how we're going to use this in a second. For R2, R2 is associated only with a positive in loop 2. R3 is associated with a negative, loop 2, but also a positive in loop 3. R4 is a positive in loop 3, and then IS is it's a negative in loop 3 and a positive in loop 1. Okay, now these values, we haven't used anything with them yet, but it turns out these are really important in doing mesh current analysis. These are important in doing node voltage analysis. If we wanted to do a node voltage analysis, we would use these values. If we wanted to do a mesh current analysis, we use these values. Okay, so this gives us 5 different equations that we can use. So here, IR1 is going to be equal to, I said there are 3 different currents associated with this, IL1, IL2, IL3. Well, IR1 is going to be equal to negative IL1. So whatever the current value is for IL1, that is the negative of that. Okay. Then we can take this next term, which is IR2 is equal to IL2. Then we have IR3 is equal to negative IL2 plus IL3. And then we have IR4 is equal to a positive IL3. And then IS is equal to IL1 minus IL3. Okay, so we have 5 different equations here. Nice. Some of these are actually derivatives of each other. You can figure that out if you really want to. But the goal is we have 3 terms here. We're going to develop a matrix that will have some matrix multiplied by IL1, IL2, IL3, and that's going to be equal to some numbers. Okay, that's it. That's the entirety of mesh current analysis. It's identical to what you did for node voltage analysis. You're just using different variables here. Okay, I don't like this because one of the issues that comes along with this is it does require planar. Let's say we had components like this, and then we also had this here, like that, and then we also had a component that goes here, but it jumps over this wire and connects to that node. This is no longer planar because we have a component that has to jump over a wire in order to reach that. So yes, you can redraw this so that that component goes all the way around, and that does create a very interesting loop. And yes, I will call it interesting, but you know, if we added one more resistor in here, or we added a resistor in here, it would nullify that. And now all of a sudden we can't do that anymore. So the planar requirement here does make this a little bit more complex, but that's one of the reasons why I don't like mesh current analysis. The other one is I really don't like trying to dumb this down from 5 equations down to 3. The node voltage analysis, we have X number of nodes, we have X number of equations, and those X equations come out much nicer in my opinion. So I just prefer node voltage analysis, but do keep in mind that mesh current analysis is another valid method. Now one of the implications of mesh current analysis here is that this current is actually a sum of all of the currents that are going into it from the different loops. Okay. So here you have loop 3, you have, oh man, I destroyed this drawing. Nice, Kale. We'll ignore those. So here we have, for component 3, IR3, what you have is you have some current that's going to be going up, going around like this, like that, okay? Some of the current will be doing it in that loop. And then the assumption is, this isn't a real assumption, that some of the other current going through that component will be going up like this and then going backwards through that component. And if you sum both of those current loops together, you end up equaling the total amount of current that goes through that component. Now this one is actually a negative. The assumption is that the current is actually flowing backward, and that's just because we do it in a positive direction. Some people really struggle with understanding mesh current analysis. Node voltage analysis is much more straightforward. But if you can understand both of these methods for solving, you have a ton of terms that are available to you. And the nice piece about mesh current analysis is if you have a current source, IS is actually one of your equations. This becomes a very easy equation to plug in because that's it. You have IL1, IL3, and they're already nicely put into here. You don't have to try to take these and say, okay, IR2 is equal to VR2 over R2. Well, VR2 is, according to KVL, VR2 is equal to VR3. So if we end up with that equation, we can combine this one into here, and it just gets gross because you end up having to combine these two. This ends up being VR3 over R3. Because VR2 is equal to VR3, this ends up equaling VR3 over R2. So if we solve this for VR3, we can plug it in to this equation to get another one. That's how you would solve for the matrix for mesh current analysis. And that's how you take all of these equations and simplify them. Okay. That's kind of a lot of material to go through. Again, I'm sorry. Read your book. And do remember, I'm not going to be requiring you to do these methods. They're a little bit more advanced, but an electrical engineer should spend some time understanding them. And if you do understand how to do these now, it's going to make the rest of this class